Hello, it's Keith here, and this is lesson 16 of the simple series of my 68,000 assembly programming tutorials. And this is a continuation from the 15th episode. We're looking again at bitmap clipping on the Atari ST. However, we've improved the algorithm this time. Last time we were moving horizontally in 8-bit chunks, in 8-pixel chunks, and that's because of the memory layout of the Atari ST. Works in bitplane, so it's hard to move in individual pixels. However, today we've got an improved version here. We've got our Chubico character here, and this time it's been wrapped with these white borders, and you might wonder why. And that's because we've now got per pixel movement, but we're occasionally losing some of the pixels of the left and right 8-pixel strip of the character. And so to ensure that the character is never partially lost, I've added an extra 8-pixel strip to the source sprite. You can see the source sprite in Sprite editor just here. So I've added an 8-pixel strip to either side. That means that we don't need to make too many changes to our code, but it does mean we're losing some of the definition. Now, if we were doing this in a real game or something, we would make those, of course, invisible. We wouldn't actually show them. But for clarity of what the code is actually doing, I thought it was better to actually show those strips of unused area. The other thing is it would be possible for us to write a version of the code which had a more complex start and end routine that wouldn't need the source sprite data altered in this way. But I just wanted to give a very basic example of how this could be done. I'm in no way suggesting that the example we're looking at today is the best way of doing this. It may even be the worst, but it certainly seems to work. So we're going to have a quick look at it and maybe it'll be useful to you. Okay, well, let's go over to today's example and let's take a look at the code. Now, we're not going to go over the bits that haven't changed from last time because they haven't changed from last time and I don't like repeating myself. So if you need to know how the general sprite clipping routine works, please take a look at the episode 15, and that also discussed things like the concepts of the theory and things. The only thing I'm going to mention this time is just to remind you about the logical units. I use a logical unit system in these tutorials on sprite clipping. I use one logical unit is 2 pixels, and that's so that I can use single byte coordinates for my x and y coordinates on a 320 by 200 screen. So that's how things work. Now, not too much of the code has changed. We're still using the same logical units. We're still loading our source bitmap address into A6 and our width and height. And the width has, of course, got wider now because of that strip of data that is potentially unused. So we've added 8 logical units. That's 16 pixels. So that's 8 pixels on the left and 8 pixels on the right. And our cropping routine will, depending on the pixel position, cause some of those to get lost. Now, the cropping routine itself, which calculates the amounts to be removed from the left and the right, the new width, the new x and y position, and anything to be removed from the top and the bottom, that hasn't changed too much. There is only one new bit, and it's these new lines here. Now, before, when we were moving, we were effectively just converting to an 8-pixel block, but now we need that extra definition so that we can do our bit shifting to achieve the not quite per pixel movement because of the logical units of 2 pixels, so per pair of pixel movement, I suppose you could say. So we're taking these 2 bits here, and if we're cropping the left side, we are E-ORing that, and that is allowing us to move smoothly when we get to the left-hand side as we start chopping off bytes as our sprite is leaving the screen. And if we just run our code here, you will see as our sprite reaches certain positions like this, there is a black strip there, and that's a byte that has been removed. And we just need to adjust the coordinates accordingly to make sure that there is no problem there with regards to the smooth scrolling. So these 2 lines have been added to do that, and that's going to be used by our code to calculate the bit shift. Now, the rest of the code we're not going to discuss in any detail because it's the same as the other simple series example, but the first part that has changed here is these lines here. Now, what we're doing here is we're getting the bottom 2 bits. That's the values from 0 to 3, which are the number of logical units, and that's the number of bits we're going to need to shift in our bytes, and we're moving that into D5, and we're converting it from logical units to a number of pixels by rotating by 1 bit to the left. So that's not going to be a 0 to 7 bit shift value in D5. What we're then doing here is we are then removing the bottom 2 bits of our X position, converting it to a byte number, and running that through getScreenPos to calculate our X position in bytes. Because there's 2 basic parts. There's the VRAM destination in bytes, and then there's the bit shift that we need to do to our source bitmap for the bitmap data we're going to transfer to that destination. And you can see that in action here. So basically our routine has changed. Before we were transferring 1 byte from our source to our destination. What we're doing now is we're basically transferring 2 bytes from our source, and then we're bit shifting them by a number of bits, and then we're transferring 1 byte from that remaining data after the bit shift to our destination screen memory. Now, because of the memory layout of our source bitmap, and because we can only load in aligned words, we're actually loading in 2 bytes and we're bit shifting those into position here. So you can see here we're loading the first byte in from our bitmap source into D0. We're then logically shifting that to the left by 8 bits, moving that into the top byte of the 16-bit word. We're then moving in a second byte from the next bitmap block byte along in the bitmap, so that will be the neighboring byte. So if you look at this sort of here, that would be the second byte just here. So we're effectively loading the neighboring pixel data. We're skipping 4 bytes in our source because those would be the other bit planes, you see. So we've now got 2 consecutive bytes of our bit plane in the word, and we're then shifting the word by D5 bits, which is going to be a value from 0 to 7 that we calculated up here. So that is effectively shifting by the offset needed by our desired X position in pixels. So that's what we're doing there. So we've shifted that source data there in D5. We're then EORing that with the screen. The EOR is of course an inversion trick. It's just we've got a simple routine that can remove the data from the screen easily for our test data. That's what we're doing there. So here we're doing bit plane 0 here, and then we're doing the same for bit plane 1, and then bit plane 2, and then bit plane 3 here. So we're shifting them all, and the only difference here is the VRAM destinations 0, 2, 4 and 6, because there are 16 bits in neighboring blocks. The bit plane 0 has a 16-bit word, and then bit plane 1 has a 16-bit word, and so on. So that's why we're going 0, 2, 4 and 6 here in the destination. The sources are 0 and 4, 1 and 5, 2 and 6, 3 and 7 for 2 bytes of the same bit plane that we need to have together to bit shift, so that we get 1 valid byte with the bit shift applied for the VRAM destination. That's the calculations that are being done there. Our actual loops and things are all exactly the same. As I say, in this way, because I've altered the source bitmap data in Sprite editor, there weren't too many changes needed to the code itself, because it's just really just that bit shift is doing it. The only disadvantage is we are losing 1 byte from the side of our screens of our Sprite in some cases. The final change I had to make is this would have actually cropped the 1 byte would have been missing from the far right hand side of the screen, and so to compensate for that I've just increased the width of the virtual screen by 4 logical units, 8 pixels, and that has corrected that. And that's how we've got, if you just see the animated GIF here, that's how we get that reasonably smooth moving example that works reasonably well. At least I was quite happy with it. It didn't take too long to code, and it's better than the horrible the blocky movement that we had before. Now I am aware that some of the later Atari STs did have a blitter built in. I've done the blitter on the Amiga. I'm not planning on doing that on the Atari ST at this time, because basically I don't have a lot of time to do programming on all these systems. At the best of times, the games that I'm porting to these 16-bit systems are really 8-bit games anyway, so I don't have any need for it. What I do have a need for is games that I can be reasonably sure will run on all systems, and so the fact that the blitter wasn't introduced at the start of the release of the hardware means that it's not something I can really justify covering at this time. Anyway, if you've liked what you've seen, please like and subscribe. If you like the videos, YouTube recommends them to more people, and if you subscribe, you'll see all the other amazing content I might have coming later for the Atari ST. I've not got any just yet, but I do plan on making more. I'm nowhere near finished on this, so hopefully you'll stick around and you'll see more later on. Anyway, hope you've enjoyed this. Thanks for watching today, and goodbye.